So I'm extremely glad to have Tadashi Takayanagi with us today. So like in the theories community, he needs no introduction at all, but as they're undergrad, so I have written down some words. So he did his master's and PhD from Tokyo University, and then he had been to Harvard and KITP at UCSB as a research fellow, and after that he's right now a faculty at Yukawa Institute of Theoretical Physics. He has received many eminent awards like Yukawa Kimura Prize at 2011, Nishinomiya Yukawa Memorial Prize at 2013, and the New Horizon Prize in Physics at 2014. Recently, just a week ago, I guess, he received the prestigious Dirac Medal this year for his the discovery of holographic entanglement formula with Shinsei Ryu. So,
okay, thank you very much for the kind introduction. It's really great pleasure to visit IISc. I remember maybe more than 10 years ago, I once visited IISc for some workshop, which at that time ICTS campus was not built. And so there's a big conference here, so I really enjoyed it. I'm very happy to recover here. So I had an audience undergraduate students, so maybe for this opportunity I'd like to talk about, the topics which I'm working on, especially keyword like quantum entanglement and also holographic calculation of entanglement, what holography looks like, and also some recent topics. Okay, so but if you have any question, just stop me please anytime. Just ask any question. So yeah, let me start with then. So I'm not going to use this projector. So I usually mainly work with this platform. So yeah, first I'd like to talk about quantum entanglement. I think many of you already heard about quantum entanglement, but this is I just give some elementary introduction. So in quantum mechanics, we can have a quantum state, which is given by some linear combination of any basic states. So I'm talking about spin, like electron spin. Spin can be up spin or down spin. And that case, up spin, let's call it 1. And down spin is 1. Sorry, 0 and 1. And therefore, usually, classical information, we have a binary number, like 0, 1, 0, 0, 1, 0, 0, 0, 1. Like classical information. But in quantum information, it's like becomes wave function. So you can take any linear combination of two different states. So A and B are complex numbers. And we usually normalize, right? Total value 1. So this is so you can allow some superposition of quantum states in quantum mechanics. And something interesting happens when you have two qubits. One qubit is this one. This one is called one qubit. Minimum unit of quantum system. That's just only 0-1 state, but the linear combination. And if you have two copies of that, that means you have if you have two electrons. So like A and B, A spin and B spin. This is a system, what we call two qubit system. And then we can consider this kind of state. A 0, 0 and B 1, 1. But actually you can put some C 0, 1 and D 1, 0. But especially, let's focus on these guys. And we especially focus on the state which is called Bell state or EPR state. Einstein, Podolsky, Rosen must consider this state. It's like given by this state 0, 0, 1, 1. This state. So this state has a very special feature. So I'm writing 0, 0 means so this 0, 0 means 0 for A and 0 for B. Okay. And so that means to combine Hilbert space, HA, AB, AB, AB. And both are up spin and both are down spin. And in this state, we have a very strong correlation. Correlation between A and B. So this correlation, what this correlation means, so if we know somehow one observer know A spin 0, then immediately a second spin, B spin should be 0. Right? These two spins the same value. So this is a very strong correlation. And the point is that this correlation only happens in quantum theory, quantum mechanics. Doesn't happen in classical theory. The reason is that this is just if we take one quantum state, this is called pure state, just single wave function, So this is actually, this means that we know whole state. This is a really fundamental state. There are no ambiguity of information. This is a precise state. This means precise, we know precise information. Whole state. But nevertheless, if total state we know, but nevertheless, if we focus on just part of the space, right, part of the system, right, just if we focus on A, we know total state for AB, but if we focus on A or B, then it's not clear. Right? So the information has some ambiguity, 0 or might be 1, and there are ambiguity of information appears. So this kind of, this is actually the essence of quantum entanglement, and this correlation we call quantum entanglement. So this quantum entanglement means, so we know the total system, but if we focus on subsystem, it has some ambiguity of information. So this only happens in quantum theory and won't happen in classical theory. This is very essential feature of this quantum theory, and so quantum entanglement is a very characteristic feature of quantum mechanics. So I'd like to talk more about this quantum entanglement. So, but in physics we want to somehow measure something, right? So this is quite abstract thing that in general, so if you have some wave function which is written in terms of some state A times some state B, in this case, we say there are no entanglement. That is a completely independent, right? A and B are completely independent, there are no entanglement, but if we cannot write quantum state or wave function in this form, then we say there is at least some quantum entanglement. But it is also interesting to measure how much quantum entanglement are there, right? So in physics, always we want to compute something. So this quantity which we can calculate to measure the amount of quantum entanglement, so amount of quantum, let's call this QE, and just QE. This is actually called entanglement. Let's put just the EP. But actually, I have to be more precise that we only focus on pure state. On total state is pure. In this case, amount of quantum entanglement is measured by some quantity, some simple quantity, which is called entanglement. Just what I will explain. But if you are interested in some more complicated state, more generic state, like mixed state, then it's quite hard to measure the amount of quantum entanglement. It is known that there are infinitely many different definitions of that, and that means we cannot choose the best one. So I'm not talking about it, but I'm talking about this pure state. And the definition of entanglement entropy itself is very easy. So this is defined the following way. We pick up some quantum state, right, for AB. We pick up quantum state, and then we go to density matrix description, which is given by this. Okay, so Brown and Kett is combined. This is a density matrix. This means the probability distribution. So you can imagine this, if we diagonalize it to some matrix, it's just 1, 1, 1, 0, 0, 0, 0. Right? This is the precise state, and other state is complete, don't include it at all. Right? So that means, we only have one state, and this means that we have pure state. Only one state is involved. If this is a 1/2, or some 0.1, 0.9, that way then it's called mixed state. Some two different, for example, states are mixed. But let's focus on pure state, and then we talk about something called reduced density matrix. So this is written as rho A, and defined by just tracing over this value into to AB. Okay. So we have in mind some system which consists of A and B. Maybe I like this. Let's write this way, AB. And let's assume observer is sitting here. So if observer can access to both A and B, the observer know everything, right? We have just a single state psi. But if the observer only probe this subsystem A, can only this guy only access to A, then this observer see this coarse grain information. Because the observer cannot see B, that means we should trace out. Just simply trace out, and this is some coarse grain density matrix. This includes everything, but this is really only part of the information. And then, so this entanglement entropy is defined by row A. X row A. This is called entanglement entropy. Maybe I'm writing it. Sorry, I'm writing it. I like this. This is the Newton union. In Neumann entropy language, this S is the Neumann entropy defined by row A, row A. So this is the definition of entanglement. This is the entanglement. So actually, this measures the amount of this correlation between A and B, and also this we also can understand this as some information. So number or amount of information which is not accessible to A. So because we trace out B, right? So observer can only see information A. So information for B is lost, and lost amount of information is measured by this quantity. So this is this takes of P. Rho log rho is like a quantum version of just this Shannon's entropy. If you are familiar with information theory, so this is if we have some probability distribution. So the amount of information included in the probability distribution is measured by this Shannon's entropy.
I have a question.
Yes.
So, do you think that the entanglement entropy itself is total, like, if you don't know the full entanglement spectrum, just an entropy that is sufficient, or some other information is also hidden in the actual entanglement spectrum, like the spectrum?
Okay. So entanglement spectrum is just eigenvalue of this. So in terms of we can write this way, but maybe we can have it again. Yeah? And then, of course, that includes all information. If we know all, entanglement spectrum, you can recover row A. But I think this really depends on what's the entanglement. But usually entanglement among we can define quantum information theoretically. That's I will explain. But using something called LOCC procedure, that actually just gives this quantity, and we don't need other quantity. So it really depends how you define quantum entanglement. But the usual quantum information definition of quantum entanglement, this quantity is enough. And this quantity exactly measures the amount of quantum entanglement. But of course, this includes more information. So yeah, let me.
So this entropy is coarse grain entropy, right?
Because with coarse grain, yeah. But from the viewpoint total system, this is still fine grain entropy. So because this entropy just comes from this guy. In this state, how many correlations are there? That's the basically. So in usual sense, we call this fine grain entropy. Because there is other coarse grain entropy. That means we can also coarse grain this state, total state, and still we can define this kind of code. That is more properly called coarse grain entropy. But anyway, yeah, this coarse grain procedure gives this entropy. So yeah, let me talk about then why this quantity is important. So if you look at the textbook like Niels Chuan, textbook of this quantum information theory, or any textbook you look, and then the following theorem is explicitly shown. I'm not going to give a necessary explanation. So what we do is LOCC. LOCC is LO is a local operation, and CC is classical communication. Right? And so you have in mind, anyway, we are interested in the case. Maybe you can imagine some spin system. There are many spins. And let's call this part is A. Right? Let's call this part is A. This is A. And this is B. And they are entangled with each other very complicated way. Originally, very complicated way. So this spin may be entangled with this guy, but also this spin may be entangled with this guy. And this is entangled with this, but also this. Right? Very complicated engineering. So in that sense, I mean, how we can understand quantum entanglement? Of course, you can calculate this formula, but this is something just given by definition. So especially quantum information, and theorists not so happy with this. I mean, they want to define any quantity in a very operational way. So I mean, the ability, some abilities we can do to some special procedure. So this is LOCC. So what I have in mind that let's imagine A and B are in some laboratory. So maybe A is the laboratory here, but maybe B is laboratory in my hometown, like Kyoto, maybe. So here is a Bangalore, and also this is in Japan. Then they are far apart, and that means we can do some very sophisticated operation inside each institute, each laboratory, right? We can do sophisticated operation here, right? We may be using quantum optics or maybe superconducting qubits or something. But it's not so easy to do quantum operation extend from here to some Japan or US or any other country, right? So then what we can do is just send some just classical information. That means you can send just email, right? You can do some very sophisticated operation, and so you get some upspin result. Then you can send this result by email to other place. So this is a classical communication. So this is a quite a nice setup, right? I mean, you can, and then the idea of quantum entanglement is that quantum entanglement should not be generated by these actions. I mean, entanglement between A and B. We are interested in not the classical quantum correlation between A and B. So that should not be produced under this procedure. So what we do is that, so this entanglement, amount of entanglement, the number of entanglement is, you can think this is somehow maximum amount of Bell pairs distilled from. So this takes some psi from this system. So this is actually quantum information theoretical definition. But actually, there's some problem if we take this, because you can talk about this one. This case is finite. If we talk about psi, AB is given by this already Bell pair, an EPR pair. So we can say this has a one entanglement. But if you talk about like more generic case, like A and B, right? This kind of set, and A is not exactly square, then not exactly Bell pair, right? So that case, we cannot extract any, even one EPR pair. Answer is just zero, right? But that's not good, right? Because we know this case is obviously no entanglement, but this case we expect some entanglement, but not as large as one. But so for that we take something called asymptotic series, asymptotic limit. So we take n copy, very large number of copies of original system, and do some LOCC, because so many numbers. So even though this kind of precisely the same as this value, so we can kind of amplify result. And finally, we take, so we compute the maximum value for Bell pair description, and we just finally divide by n. And so, that we take a limit, n goes to infinity.
Are these local operations unitary?
Okay, the local operations are unitary or projection measurement.
Okay.
Anything you write, basically. So you can add extra bit and do some measurement, and also up to unitary. That's kind of thing, yeah. So, and anyway, yeah, so this is the definition of entanglement from operational. This is quite operational. But the important theorem, which is proven in this quantum information context, that the proof is not so difficult. So if we are to just look at that, it's not very elementary calculation. This is precisely agree with this guy. This is exactly the same. So that is the reason why we think this formula is useful and really measures amount is.
What do you mean by this two?
This is okay, sorry. So I should explain. So we have this kind of system, and we act LOCC, local operation and classical communication, and in the end want to become just kind of like this number, some number of Bell pairs. Just like this. So this guy is Bell pair. It's right like this. A and B. So yeah, in other words, this three means you just get some number of Bell pairs. Some number. So once you get some number, we can say that the entanglement, there are n unit of entanglement. So this is what this means. Okay.
Sir, is there some existence theorem which proves that by applying LOCC we can always reduce two systems into Bell pairs?
Yes, yeah. Always we can extract it. So that's a you can explicitly show. Because in general, it's like some you can expand, side to some copy, right? Some n number, right? And it's like looks like this, maybe A00 plus B11, right? To some power n, right? But you can expand this, like this. Then you get a 0, 0, 0, everything 0, right? And then to some power, and you can expand something like this way, and this is not this, but the interesting is m minus 1 b, and then 1 0 0 0 0, and then okay. So these guys all appear in the copy, right? So let me write it here. So there is a term which looks 1 0 0 0 0 0 for a. So this is a b. So and 1 0 0 0 0 0 b. And also you can add 0 1 0 0 0 0 and that way, right? A B, and you can extend this way. So only one entry is 1, right? And other entries are all 0. There are n such different, n different. This is first one, second one, and the nth one, right? In the end, it's 0 n such copy. And this guy is a maximally entangled state. So we know this has a log m entropy. Right? And if you just talk about just the first one, this is m to the m minus 1 b, and m to the nth power is like 0, 0, everything. Right? This is no entropy at all, 0 entropy. And this case is log m entropy. And you can repeat this procedure, right? M minus 2b squared, and you have also some number appears. M2 or something, like some number appears. And the good thing is that LOCC we can do some projection measurement. So you can project down to this state or this state or this state. So then once you project down to this state, it's just already like Bell pairs. So you can say Bell pair is log m Bell pair. So that way, but it's a probability distribution. We have to multiply this kind of factor. So taking average. So I should say it's the average. We take a maximum average. Then we reach this one.
So you have to take partial traces in a particular fashion to make them Bell pairs after this expansion.
Sorry,
Partial traces, like
but sorry, here we don't act. Okay, so B is always present. Yeah, B.
Yeah.
We only act projection measurement for because it's that should be only act for
right.
yes. And that's enough to extract. And also you can. So this is the question. Point that this is turned out to be SA. This is a very important theorem. But you can also go opposite way. So if we prepare SA number of EPR pairs, you can reconstruct original state. So actually there is a opposite direction. So it's a reversible. So this is in terms of thermodynamics, this is a really equilibrium situation. So this is good thing because this only happens when this state is pure. But if we talk about mixed state, this is no longer true. It's not. It's like no equilibrium situation. It's only one error. But in pure state, very nice story happens because of this. So that's the reason we can also claim that this is the best quantity to measure quantum entanglement for pure state. Okay, so now I go to more quantum field theory, more high energy oriented consideration. I'm working on string theory all the time. So would like to relate to quantum field theory and also in general to holography. So now, now entanglement entropy in, so it's quite interesting to think about quantum field theory. Entanglement entropy in quantum field theory. So my notation d plus 1 means d, there's a one time direction and d space direction. D plus 1 dimensional quantum field theory. And then there is a very famous fact is known. So to calculate anyway, how to define entanglement entropy. So we decompose, this is a time slice, let's take t equals 0. And you can do, this is a space manifold, space. And this time direction is also one, I don't like it, space direction. And we just call some region A and other region B. So we want to separate universe spaces to ATA times AT. So this is what we did, right? Always we are doing this. So then, once we do that, we can define, right, rho A and we can calculate the entropy. And quantum field theory, this really factorization is very subtle issue. And if we are very rigorous, if we want to understand some rigorous aspect, you should look at algebraic quantum field theory. So, but I mean, let's forget about it. I'm always putting some UV cutoff because the quantum field theory has an infinitely many degree freedom. Always UV divergence there. So we want to put some UV cutoff. So that means we have some lattice system. We are considering some lattice system with some lattice constant. So it's like a spin, a lot of spin, infinitely many spins, but there are actually discrete degree freedom, and the spins are separated by issue. So that case, anyway, so if we talk about the entanglement entropy, so people computed this, and it turns out that it's a UV divergent because quantum field theory have an infinitely many degree freedom. So epsilon in the UV cutoff, and so it looks like this. It's B minus 1, and area of this. It is a boundary of wave, not the volume of wave. That's the point. So it's a boundary. Only this boundary plays very important role. And some constant, let's go gamma. This is only depend on the theory. And subrating time.
Is it prototype the ground state or is it prototype the ground state?
Okay, ground state, yeah, I'm going to ground state. But you can also slightly excite the system. You can go to finite temperature, or even finite energy excitation is fine. So any finite energy state satisfies this area. It's called area. This area, so this is called area.
So if you have three regions, like you divide the B region, like drawing a line like this, and this is B and D, this is C. So then the entropy of A, like SA, will be what, like?
Sorry,
then,
B
then
is sorry, like this or?
Yeah, and draw the A.
So A.
Yeah, draw the A in between.
A B.
No, not like that. Three regions I'm saying. One A, B, C.
A B C.
Okay. Yeah.
Maybe like this.
Yeah, like that.
Okay. Yeah.
Yeah. So then entropy of A will like the boundary of A will be like it has a boundary with two different regions, right?
Mm-hmm. Yeah, but that case anyway. I mean, if we talk about the entanglement entropy is always defined by just bipartite system. So if we talk about A and correlation between B, C, then the same thing, right?
Not only B or only C, like that.
So if you want to do, the question is B is okay, but do you combine A and C?
Oh.
Always you need to complement.
Okay.
Yeah, okay. So that case, you can do it. Then area along with this is proportional to this area. It's always by times. Anyway, so this is the point is that this entropy is proportional to area but not the volume. Like usually thermodynamic entropy is proportional to volume, right? But this is not true. So it's not because this actually comes from other reasons. So SA, we define the entanglement entropy as SA. It actually cannot be SP. It's the same. These two are the same.
What are the other terms apart from the area? Plus dot dot.
Okay. So you can write down. Let's assume this is a smooth boundary, not like Casper thing. Then it's like you can derive it's a two-dimensional one, and you can Taylor series like by, and then here, roughly speaking, what you get is also dimensional reason. It's like actually square root g, and this is, you can think this is square root g, just the area, right? So just boundary of A, and then it's like now we have curvature, and also like some extreme curvature term. Because the K is dimension 1, and R is 2, so it's like something. So you can imagine, right? That way, all divergent piece is like this kind of local integral, just higher curvature term. But if we end up with some finite, this is very interesting, right? This is highly non-local. It's not cannot be written this kind of very simple geometry. This has a lot of information, of quantum information.
So are we talking about curved space-time now?
Sorry?
Are we talking about curved space-time?
Curved space-time?
So are we talking about space-time, flat space-time, or curved
Yeah,
space-time?
anything you're right. Yeah, I mean, yeah, this is also true for curved
So
space.
I mean, is it possible to factorize the inverted space in curved space-time?
Yeah, also same thing. I mean, but of course, in quantum field theory, to factorize because you need a UV cutoff. You need to, lattice regularization, and that also can be done for curved space-time. So essentially, that's the sense.
Yeah, and the entropy depends on the UV cutoff of the theory.
That's right. That's right. So yeah.
So if we are interested in some small region in some curved space-time, so can we talk about the Hilbert space in terms of the Hilbert space or in terms of the operators in that small region? So if we are interested in some small region in curved space-time, so can we talk about the Hilbert space of inside that region, or we talk about the operators in that region?
Yeah, but you can just talk about some. So small means how much small, but if this is much larger than epsilon, then you can talk about Hilbert spaces in this region. Okay. But yeah, if you want to remove this cutoff epsilon, then you need some algebraic operator rank. But then not good because this is not well defined. Entanglement entropy is not well defined.
Because like I heard that the factorization of the Hilbert space is not true in when we include gravity. The factorization of the Hilbert space cannot be true in that case when we include gravity.
Okay, yeah, but gravity, if we couple gravity, situation actually improves. Okay, so if you are familiar, if you are interested in this more rigorous approach in algebraic quantum field theory, first of all, if we want to define entanglement entropy in quantum field theory, usually quantum field theory is something type 3 algebra, where we cannot define entropy at all. So it's just divergent. Because it's an epsilon goes to 0, it's divergent, mathematically this. But if you couple to gravity, situation is improved. That is called type 2 algebra. Then, I mean, we can actually define it. The main reason, so maybe that's the point where we mentioned that. Before I go to the follow. Okay? So, this is also related to the reason why people look at this area in very early time, 1986 or so. Solkin and collaborator looked at this. And at that time, people wanted to understand this black hole entropy. So let's compare with black hole entropy. Now, black hole entropy also, this satisfies some area, vacation talking area. So people are excited that because this entropy also area, and also black hole entropy is also area. So black hole entropy is given by this area of horizon. Let's call horizon sigma. 4 G Newton constant. This is a well-known vacation talking formula. And there is an analogy. So the reason people look at this problem, right? This problem, why people look at this problem is really to understand the black hole entropy. So if you have a black hole, of course, observer cannot see inside the black hole. So some amount of information hidden there, that is measured by this. And on the other hand, we are talking about this quantum field theory calculation. So then we talk about subsystem. Let's call A is outside because they say and SB is same. So let's talk A and B is inside. And observer is sitting here. Right? Observer cannot see inside. So that's the reason we get the entanglement. Both are somehow nicely proportional to A. But there is a severe difference. There is a unique divergence here. And yeah, in rigorous way, so this is not well defined because of divergence. But if we talk about gravity, it's like just finite quantity. And another thing is that coefficient also universal, right? Just fixed by Newton constant. If you can put some scalar field or fermion around, but still this one is true. But this is not true. So if we have twice number of fields, then gamma becomes twice. This is gamma is proportional to number of fields, basically. Because entropy is extensive in that sense, only about number. So it's quite different. So that time is not completely understood, but there's a one nice connection that is actually given by the fact that if we couple gravity, something will happen. So if we compute black hole entropy, this is true, but this is a three-level contribution. What about one loop contribution? Right? It's like you have some field around them, then you have a one loop contribution. So this is one of the G Newton is like three level, and one loop contribution is order one, right? And two loops, G Newton. This power, right? I mean this power series of Gn appears, and one loop contribution is exactly same as this type, right? Calculation. The metric is a little bit curved, but forget about the metric. Then what we just integrate out, trace out b. That's exactly the same calculation of this black hole entropy. So you get epsilon d minus 1 and area of area sigma is here, right? So that is actually area sigma with some coefficient maybe some here. So actually this is something good because this is a UV divergent, but you can renormalize, right? Newton constant. In quantum physics, we usually renormalize. So this is a bare Newton constant is 0, right? Plus gamma. So once we do that, then this just gives nice formula, right? And this means that entropy is well defined, right? And this is the reason why if we couple gravity, something will happen. And also that resolved also all the discussion about this. But nevertheless, I mean, in this discussion, we have this nice story, but this part is missing, right? What's the connection to this part and entanglement entropy? That is, entanglement is really related to this one-loop question. So how can we understand this? This is only can be answered by looking at hologram. That's I explained. Yes.
So this entropy is the thermal entropy, right?
This
Yeah.
This is thermal entropy. This is come from purely gravitational entropy. So this is a thermal entropy.
So,
I mean, because black holes, as you know, black holes are temperature, and this is thermal entropy.
So this thermal entropy is the same form as the entanglement entropy. So
Yeah,
is
yeah,
there
yeah.
a connection between these two?
Yeah, because it's the same thing. Because here we have a thermal circle. You have usually, I mean, sometimes we take a data X, canonical number. This data is periodicity around here. And we do the same thing. To calculate entanglement entropy, we compute this first, some power of n, and take derivative of n. Right? So replicate. That's exactly the same because you can regard this as A, say some modular Hamiltonian times n. This is the inverse temperature basically. So this calculation actually is same. Makes sense.
So this thermal entropy arises only because you make the space-time discrete like this triangle lattice over there, right? So what was your motivation behind like imagining space-time as lattice?
Maybe cut off.
Oh yeah, without cutoff, it's this.
Yeah, that's what I'm asking. Like, why did you want to measure the entanglement entropy in space-time?
So why we want
Like entanglement entropy was previously defined for quantum systems, right? So why did you want to measure it in QFT?
Oh, okay, well, same thing. QFT has a quantum state.
Yeah.
And that's just definition. From QFT have a wave function instead of wave function. And entanglement entropy or this wave function are just given by this guy.
Yeah.
And anyway, the main reason, I mean, of course, why this reason? I mean, well, originally we wanted to understand black hole entropy. Another thing is we want to characterize degree of freedom of vacuum state. So then we can see this constant turns out to be related to some central charge or some universal quantities. Anyway, we want to treat the quantum field theory as much as universal as much as we can. That's the thing. Universal description quantum field theory is based on quantity is entanglement. Yeah, of course you can calculate the energy or but that's only one information. But if you can change this side, right? And there are a lot of information included here.
Yeah. And this thermal entropy deeply depends on the UV cutoff. So how do you decide the cutoff? The cutoff, the value of epsilon. How do you?
The cutoff is just you can put by hand.
Just by.
This is the same as the lattice gauge theory.
Ah, yeah.
Okay. Right. Okay. Yeah, so I mean, if you talk about gauge theory,
Mhm.
so there's a nice, quantity like Wilson loop.
Uh-huh.
But Wilson loop only defines gauge theory, right?
Oh, yeah, right.
But if you, what about more general quantum theory? What's the analog of Wilson? This is actually mass.
Okay.
This is actually one way to understand. Most in condensed matter people also look at this,
Mhm.
and because this is something easy to calculate in numerical. So maybe this looks tough in quantum theory, but this is something you can easily calculate if you know some even numerical wave function.
Mhm.
So in terms of spin lattices, then you can just calculate because just we just trace out the rho and just compute rho and like
Right.
this, and then I mean we can easily read some value of central charge and the basic information.
Mhm.
So that's another.
Yeah.
So if we know really detailed theory, we need to go beyond this one. But if we have some theory which we don't know, then first thing to do is to calculate entropy.
Yeah.
Then you can get some nice information.
So does the central charge corresponding to this QFT depends on epsilon?
Yeah, no.
Central charge.
This also logarithmic term. Okay, so let me go to this CFT. That means 1 plus 1D critical point. Like you can imagine some transversalizing model. Maybe you learn in some textbook. So 1 plus 1 dimension, 1 time and 1 space. Then this entanglement entropy has a very special behavior. So log
Right.
A log epsilon, right?
Yes.
So subsystem is A is just the length set. Then you can read of this is the universal because it doesn't depend on epsilon. It's a coefficient. You can change epsilon, right? But the 2 epsilon, but you just get constant. You can easily distinguish.
So the amount of degree of freedom present in the system depends on how you make the lattice.
Yes.
Okay.
Yeah. So it doesn't depend on the lattice.
Mhm.
So you can change the lattice structure, then you get some shift here,
Mhm.
but this coefficient doesn't change. So central charge is universal.
Yeah.
It doesn't depend on any discrete.
Yeah, that's what I'm asking.
Yeah. No, so it doesn't, right? Doesn't. But this guy depends.
Okay.
So there are many. Some term is affected by lattice structure, but sometimes not.
Mhm.
So this is exactly. Okay. So now let me go on to holography. So anyway, the motivation is to, actually this was our original motivation. I want to understand this guy in terms of some entanglement. So for that, actually, we need to go to talk about some holography or more special line for CFT correspondence. So maybe some of you are familiar with CFT, but some of you are not. So how many people know CFT? Maybe, yeah, okay, half of us. Yeah, it's but sorry, I'm not going to details about it because this take a very long course and CFT. So I'm not talk about it, but I just want to say the claim of this CFT. So this is founded by Marda Sena, 1997. So this is a very surprising equivalence between gravity and some quantum system, especially conformative theory. But holography originally tells us that so black hole entropy is area law, hollow area law. So this means that degree of freedom, number of degrees of freedom in gravity, d plus 1 dimensional gravity. The black hole is supposed to be a maximally entropic object. So, we can put anything inside some region, and we keep this adding many things, and then finally it becomes black hole. So it's maximally entropic object, black hole. So such an object have this area law. That means maximum information which accommodated some region is actually proportional to area. So this is proportional to area. So area. So that means this area, of course, area is a bit surprising because usually entropy is like extensive. In some times it should be proportional to volume. But area, maybe you can view area as some volume in lower cell. Volume in d-dimensional cell. Some quantum system. We don't know exactly what this quantum system means, but some quantum system in d-dimension usually has an entropy which is a volume, which is given by area in d+1 dimension. So we have some black hole, and we have some entropy proportional to area. But if in terms of the object, right, which really localizes the boundary of black hole here, it looks like volume. Entropy becomes volume. So motivated by that, this holographic principle was proposed, and let me write here. So holography. So holographic principle says that d+1 dimensional gravity, this can be of course quantum gravity. So gravity on some manifold md+, let's call it md+1, is somehow equivalent to d-dimensional quantum system, quantum matter, which lives on boundary of this m+1. So it's like some gravity here, and its boundary is like this here. So some quantum system. Quantum system is lives here, and gravity is here. This is something called holography. This holographic principle. This is proposed by Tokuta and Sasuke. And later, so this looks very philosophical. Maybe it's not very ambiguous. But of course, if this is true, so of course we can understand this origin of area entropy. But later, few years later, actually, owing to some developments of string theory, we could find some express example, nice example of this holographic principle. So that is called area CFT correspondence. It's formed by Madaseno in 1997, using some more sophisticated language in string theory like D-branes and so on. So this is a bit ambiguous. I mean, gravity on some manifold, but what kind of manifold? Right? So we hope this is true for any manifold, any space-time, but at least this can be precisely kind of confirmed for particular manifold called anti-Loschita space. So the dimensional gravity on ADS is anti-Loschita space. Anti-Loschita space has a negative curvature and the maximum symmetry, or in other words, cosmological constant is negative. And this turns out to be equivalent to d-dimensional conformal field theory, CFT. It's called conformal field theory. So conformal field theory, you can, if you are familiar with that, fine, but if you are not familiar with that, so in condensed matter language, it appears as a critical point, right? If we take some, if there is a second order phase transition, it often happens that it's some gapless theory which is given by conformal field theory, or if you learn about the free, for example, scalar field theory in field theory textbook, you can imagine this CFT is like some massless quantum field theory, just quantum field theory with all particles with massless. This is all masses there. Some such as gapless theory, or Maxwell, I mean, electromagnetic also, because photon mass is zero, so it's quantum field theory. So so ADS-CFT tells us that, so special manifold, which is called ADS, it looks really like this. So I can write this picture, but I can also give some metric metric is like this. So there are extra dimension for z direction and d square and dx, maybe explain dt square and dx square and some d minus 1 square. So this looks like Minkowski space, right? Minkowski space, but with extra dimension, z direction. Z direction. Here it's if we fix z, right? It's like Minkowski space. And the point is that so z as z goes to large, right? Its metric gets small, right? Smaller. That means shrinks, right? To zero side, let's say. But what we call boundary is always this is boundary. Boundary is important. That this is a bulk and boundary. This is called bulk. Bulk gravity dual to boundary. So boundary is situated at z goes to infinity. Z goes to infinity. So z goes to 0. But problem is that z equals 0 is this is metric divergence, right? And this divergence is exactly the divergence which we have in quantum field theory. Right? In quantum field theory, we need a renormalization, right, to compute something. So because of that, so this is 0, but we put some epsilon. We put some epsilon. We usually limit to some region, epsilon. Epsilon is a UV cutoff. Cutoff of conformity. So anyway, geometrically obvious, but this classical geometrical divergence actually becomes just quantum divergence. This is an interesting point of ASFT. Something classical here becomes something quantum. So this is a really essence of it.
So you send z to 0 to get the CFT. So that you are talking about ADS boundary CFT correspondence. So in to get this like that's this boundary like gravity.
This boundary, right? This boundary is this z equals 0.
No, I mean the boundary conformal field theory.
Boundary conformal field theory, conformal field theory with boundary, or this conformal field theory.
I'm not talking about this one. So that day you are talking about like the boundary ADS boundary conformal field theory where you construct another boundary like this boundary of the gravity, not this one. Right?
It is BCF.
BCFT.
Okay. BCFT is let's write it more 3D picture. Okay. So like this. So we have like this is the original ADS CFT set.
Right.
And if you want to put some real boundary also CFT like this, you can cut this. Cut it a meter. Then you have an additional surface appears.
Ah, okay.
So you have you can so this is under the surface. There is okay, so this is a boundary, right? And you have a z direction here.
Yeah.
And you cut this, right?
Right.
Then there's an end of the word, right? It appears.
So what's the boundary in this pointer patch?
You can just set it to x1 equals this.
X1 equals.
This is just to give
oh,
you
okay.
very simple. No. Okay, that's a bit advanced question, but yeah. Okay. Yeah, I'm not talking about CFT. Okay, but anyway, so this is a CFT setup, and the idea is so you can see some symmetry, at least one basic symmetry, z and x, I. You can multiply lambda, no? You can multiply everything lambda, and this cancel here. Right? This is a symmetry, right, of the space time. This symmetry is really scale invariance, scale transformation, scale invariance. So the theory is, as I said, massless theory. Conformal means, roughly speaking, scale invariant. You can change the scale, but still the theory doesn't change. And this is explicitly can be understood from this property, and that also shows that z direction plays a role of length scale. Because you also change, this changes at the same time when we change x length scale. So z direction, you can regard this direction length scale. So what we are doing in ADS-CFT is that we have a very complicated quantum state here. The quantum manifold is very complicated. There are many, different correlation or entanglement, short length entanglement and long wavelength entanglement, and they are mixed. But we do some Fourier decomposition. Like short wavelength thing is appeared here. Short wavelength correlation is here, and long wavelength is here. For example, if you excite the system, it's at a very low energy, and you have some quantum material, just some slightly excited, little bit, very weak energy. Then this part is modified. This part doesn't change. It's a UV. Here it's a UV, short wavelength of IR. Small here, if it's slightly excited, then gravitational wave propagating. But if you really very sharp, very strong, high energetic excitation, then you can change this picture. So basically that's what.
So in the CFT that is living on the boundary, so that has a volumetric entropy.
Sorry, what did you mention?
What is the how is the entanglement structure of the CFT?
Entanglement, I will explain how to calculate entanglement.
So that is volume or area with respect to the CFT, not with respect to
It is an area, so area. Both area. So interesting. The bulk is area, but also boundary of area. This is because of this method. Yeah, I will come back. Yeah, that's a very important point. But I just here I wanted to talk about it. Yeah, now I will explain that. So now let me talk about this and now get back to entanglement. So this now we talk about entanglement. So that's the holographic calculation of entanglement. So anyway, we wanted to calculate. So see, ADS-CFT means ADS gravity. Gravity d plus 1 dimension is equivalent to CFT. D, right? And the CFT we can define entanglement entropy. Rho A. And then what is this counterpart in gravity side? So usually we can calculate many, if we want to calculate energy, right? Energy of this state, then you can calculate gravitational energy. They agree. And also black hole entropy, so you can calculate black hole entropy here, right? Just area, this formula. And that agree with thermal entropy in the CFT. And this is a kind of generalization of that. So more sophisticated entropy. So how can we calculate entropy? And it turns out that this guy is given by a very simple formula, which is like this. And now let me write a picture. So we have same quantum parts, and we sum is A. Right? Yeah, okay, let's go this. And then actually it turns out it's like minimum of some surface called gamma A, area of this guy, and for B. So gamma A is some surface which just end on boundary of A. Okay? Gamma A, boundary of gamma A is just boundary of A. So there are of course, many different ways to extend this surface, and we have to pick up one of them, and that's given by surface with minimum area. And the point is that, so we have this metric, right? So this metric is very important, right? So, because if you want to talk about something like this, in flat space, right, minimal surface obviously coincides with the boundary. But in an ADS metric, right, if we go a little bit large Z, the area decreases because of this factor. So it's better to go inside. So that way, we get a non-trivial surface appears. But this is true for static system. Assume. Static areas. And we take that means we can take time slice, some time slice. It takes time slice, that means we actually impress with T equal, because I'm talking about statics, no time dependent. Let's assume space-time, anti-Doshita space, this space-time, or you can slightly modify this pattern. Maybe you can replace this with a black hole, but still, Churchill the black hole is a static, right? And you can still you can apply this formula. And because we can take T equal always time 0, T equals 0, and everything is space-like, everything Euclidean, and you can find minimum area. Okay. So this is actually how we can calculate entanglement, and you can confirm this precisely produce many different properties. Like area rho is obvious, right? Because metric like Z square, right? Like this, I wrote it here, there. And that means it's divergence, right? If you compute area, main contribution just comes from here. Because metric divergence is one. So that means it's obviously proportional to right, area. So that explains area. And there are many, also SA equals B, this is also already obvious, right? If we put some B here, but the whole entropy for B, of course we have to use the same surface. Because this separates area. So that way you can also, you can derive more sophisticated results by computing, especially two-dimensional formula. Hirschi also Ryu-Koizan Mardasena was able to derive this formula from bulk to boundary relation. That means CFT partition function is this basic relation, bulk to boundary relation. It's basic combination, basic consequence of relation is ADS gravity partition function equals CFT partition function. By using this, you can derive also this formula. Anyway, in many ways you can justify this equality.
So what kind of states in the CFT does the black hole in the space-time correspond to? Like
Thermal state.
thermal states.
Thermal state, yeah.
Okay.
Finite temperature.
Finite temperature.
Finite temperature. If we talk about just that, yeah, like this. Finite temperature.
Yeah.
Then
What would be extremal black holes?
Huh?
What are like extremal
extreme, you can also put charge, energy and charge, and then energy equals to charge. Almost the complete. Then you get the extreme also in ADS. And then you have a ADS2 structure. But of course, extreme block also already there in flat space. Also. But you can also. Okay, so then, and also one more interesting and simple fact, property we can derive is something strong subordination. I'm not going to take a strong This is a very important inequality for entanglement. Let's take some Hilbert space ABC. Now you can also add something more here. This is true for any state, even without assuming any pure states. So A, B, C, D. I write A union B as A, B, like this way. I'm using this notation. And then it's AB plus SBC is always greater than ABC. This guy. And also there is another one. You can also easily prove this. A and C. These guys are called strong subadditivity. This is always true for any quantum system. And but its proof is very complicated. If you need some complicated linear algebra, deep and collaborator, blue sky proved this quite long ago. It's very famous inequality. And I think most important inequality in entanglement entropy. And you can think this is a kind of analog of second law of thermodynamics. Second law of thermodynamics is entropy is increasing. But essentially this is the same thing. So actually you can easily derive this from holographic calculation because this is easy, so I let explain. So this is the extra dimension z direction, and you have A, B, C, and the minimal surface for SAB is A union, you get this one, right? BC is this one. Right? And the sum of these two surface area is given by this one. And on the other hand, what is this guy? This guy actually, you can see that obviously ABC. So you can say this part, this guy, right? This guy covers ABC, and this guy covers B. But there is a data surface which covers ABC and B, right? Obviously. So this area should be smaller than this very funny area because this is a minimal area by dimension. So this gives you precisely this inequality. And you can also show another one, ABC. So you can now regard this guy, this funny guy, as some surface which cover A. This guy covers C. So that means there is obviously a data surface, which proves also second equal. So this is that way. So this is also another, similar advantage of ADS-CFT. So ADS-CFT makes originally algebraically very complicated property of quantum mechanics for CFT into some geometrical language. This is just triangle equality. It's very, that's a benefit to consider ADS-CFT. And also we can generalize this case where we remove this constraint. So if this is not static, then what we can have, what we get is like this time dependent version. my work with Veronica Kubeni and Mukund Rangamani. This one is my work with Shinsei Ryu, who is a condensed matter theorist. But Veronica and Mukund is, I think, India. We met in, originally we met in Harvard when I was a postdoc at Harvard at that time. And at that time, so my post researcher was Shiraz Miwara. And he invited many Indian excellent researchers. And one of them is Mukund, was there, also Veronica there. And really enjoyed. And we met actually each other in this conference in Puri, actually. 2007, so 2006, in Puri there is a nice Indian students meeting, and we met again, and we started this collaboration. So it's really nice to always visit. And so, yeah, so this is time, so this is good, but this is only can be applicable to static spacetime. And if we talk about time dependence, there is a big problem, right? So it's a Lorentzian spacetime. So minimization, this is not good, right? This is really bad because if we go to right direction, right, the area becomes zero. So I mean, in this t and x, right? If we go this surface becomes this area equals zero. This looks like minimum, but I mean entropy is zero, right? Then it's trivial. This is obviously not correct. So what we can do is to slightly modify this formula. And we had at that time we have many candidates, but in the end we end up with this final correct one, which is given by this. Forget about the minimization. We just externalize this area. So for G Newton, and so yeah. So anyway, we cannot minimize. So we just pick up many different surfaces and externalize. Just take a saddle point. And but sometimes there are several solutions, especially interesting when there is a non-trivial phase transition. We have several solutions. So basically, we solve, right? And this I think you do this many exercise, right? Variational principle, right? Minimal surface, extremal surface in Lorentzian geometry. So, but if there is several candidates, we can take a minimization among them. So this minimization just do down for a discrete number of set of solutions, maybe 2 or 3. But anyway, so this formula you can apply this in a fully Lorentzian time-dependent case, and you can get correct answer. And of course, it's time-dependent. You know, so it's like ADS or maybe let's remember the previous one. So there are non-trivial time dependence, right? So then there is a time direction at the boundary. So you can choose subsystem A here or here. This is t equal t1, this is t equal t0, right? And you calculate this minimal surface, extremal surface. Like it depends on the time, right? Non-trivially extended, and the area also is time dependent. This is the way to calculate in that time dependent case.
So in this picture, the time A spans both space and time in the CFT perspective. It has range in the time direction, the region.
Time direction.
But here it is 2 different time slices where there are 2 x.
So this is just time. I mean, just time and just x direction. What I wanted to write. Here is no time, right? No time. It's a completely Euclidean. And t equals 0. We set t equals 0. So just x, y.
And here it is looking like a surface. So is it actually a line in this?
Okay. So this is like I have in my ADS form. ADS form because we take time slice t equals 0. It looks like 3D, right? So it's like 3D. Here I'm writing picture in so that it's ADS 3. So always gamma A is codimension 2. So ADS 3 case it's like curve. But ADS 4 case it's okay, sorry, yeah, so sorry about confusing. But then anyway, like this. So, and then, yeah, one more point, I should emphasize that, so related to the previous question. So if you have a small region, right, then it's a minimal surface like this, right? And indeed you can see small UV, so this includes UV information. It's really right, nearby boundary. But if you have infrared deformation, it's like extended. So that also, I mean, can be understood as z direction as a time scale. Okay. And okay, so So let me, okay, so maybe let me post the final copy.
So is there a particular set of properties that a space-time should satisfy to have a holographic role?
Good question. Yeah. Yes. So okay, so maybe let me mention. So when holography works, right? Okay. This is not completely, I should say, I mean, yeah, so this is not completely understood actually, but at least we know some example where we can understand better. Because I hope that maybe generic, even generic quantum physics, maybe some sort of holography there. That's my hope.
Okay.
But what so far has been accepted, many people, it's like this.
Okay.
So I'm focusing on ADS safety. So I'm focusing on ADS safety, and but ADS safety, we have strong weak duality. So that means we know that. Okay, what's the
So you mean something like S duality?
yeah, sort of.
Okay.
Yeah, I understand. So this is a more sophisticated understanding. So there is a two coupling constants in ADS-FT, major coupling constants. One is like this. Yeah, so ADS has a radius. So I didn't write it, so but ADS has a, in the metric I should write this ADS metric, ADS radius. So that is necessary for this. Okay, so I just only wrote this way, but there is actually a factor, ADS radius. So that means size of the ADS. But just calculation, you can omit this and you can recover it. So I didn't write it. But this radius is very important. If radius is very, very small, right? So universe is very small universe, you expect a lot of quantum correction, like quantum gravity. So we can compare this scale with string scale. Because anyway, ADS actually comes from string scale in the background, and string scale, and there are other like ADS radius scale with Planck scale. And you can take maybe just quadratic power, and this actually turns out to be, you can calculate something like the, and this is, yeah, GG and but this is something for calculate. So yeah, okay. So let me. Okay, so I'm talking of the special setup, right? Where, for example, ADS5 process 5, ADS5 is CFT4, but this case is like 4-dimensional Yang-Mills theory. Yang-Mills theory. It's gauge group, and gauge theory is SU n gauge theory. And this n is rank of gauge group.
Yeah.
And there we notice that this should be right large if we want to keep some classical gravity. Right? ADS want to be very huge, but not necessarily. Now you can, if you are interested in quantum gravity, it's fine. You can set it to 1. But to understand better, at least we know much about the classical gravity. General, if we want to use some general relativity, then this guy should be very, very large. And then n should be large. Right? N should be large for this classical gravity, and also this guy should be large. These are the condition for classical gravity.
What
So-
happens if lambda is small?
Lambda is sorry. This is also should be large, right? Because string scale and you have a.
But what happens if like R radius is greater than Planck length but less than string length?
Okay, this is the very stringy. So yeah, if you can deal with string theory, you can compute even.
So it doesn't depend on the Yang-Mills coupling at all. Like, if n goes to infinity, that thing will always go to infinity.
Okay. Yeah. But you can also say that. Yeah. You did that. Right.
So like.
But usually there is some traditional Lagian gauge theory. That approach, this goes to infinity, but this keeps finite actually. And then you can have a better property. You can control some main function, good property. So that's the reason. Usually you said then goes to infinity, this is maybe very rare. But actually you're right, I think you can. Exactly. And this is a condition for practical. Of course, we might be interested in quantum gravity, but usually we start from classical gravity and put some quantum correction. And that case, we reach some quantum gravity. If we think that way, we pass in this that and slightly, loosen these conditions. This is the usual idea. And yeah, this is and if we talk about really quantum situation, maybe N can be 1. But there are no way to precisely test it, right? Because we don't know quantum gravity at all. But maybe formally you can define quantum gravity. Maybe for 2, 3. But so the question, so how when holography appear works, usually we assume some classical gravity approximation to it. So if we assume classical gravity approximation is good, so in general, if we want classical gravity, classical ABS gravity, we expect, then we need, and there are 2 things. One, large degree of freedom. This is a large n limit, right? Large n limit. Large degrees of freedom. And the second is strongly coupling. So this is strong coupling, right? This is a Yam's coupling. This is strong coupling. These are actually this side. And so large degree of freedom, so you can, in a 2D CFT language, this means large central charge. Large N, also large central charge. And this means that somehow coupling constant goes to large. This is to identify. So why these are important, right? So this condition, strongly coupled, is very important because if we don't have strong coupling, just only large number of degree of freedom, you can imagine some free theory and infinitely many copy of free theories. And then that doesn't look like any classical gravity. Because if we pick up some many energy levels, there are many low energy modes, which looks like higher spin. Right? Spin is much greater than 2. In general relativity, we have spin 2, right? And spin 3 we don't include. In string theory, there is spin 3, but it's very highly excited, highly energetic. So this is necessary for that. And this is obviously we need to make this ADS radius very large. This is, I think, very intuitive. So space-time is very large. So anyway, basically these two.
So does the d-zeta space time satisfy these two conditions?
Logita space.
Yeah.
That's another thing. It's not clear. DSCFT.
Yeah. I'm asking that if does DS satisfy these conditions? Like, does is DS expected to have?
It's not clear. Not clear.
Okay.
Yeah, but I think in general, but C should be. But maybe I can let me. That's a very advanced topic, I should say. But it's like currently ongoing subject. Nobody knows the precise answer.
Yeah. But people have been looking into it, so that's why.
Yeah. So of course this is all about total ADS CFT, and ADS has a negative cosmological constant, and so but in phenomenological reason, inflation or even current universe, many people believe cosmological constant is positive, very small but positive. So there we have Logita space, right? So this is cosmological constant, then maximally symmetric space-time is Logita space. Space-time, that's DS. Right? And then it's quite natural to think about this holographic gravity dual of DS. So DSCFT, that's DSCFT. This was first proposed by Stroming, 2001 also. But there is a proposal, but we still don't know much about this because of the following reason. There are many reasons, but let's see. So this is good proposal. This claims that d plus 1 dimensional gravity is equivalent to, because also symmetry reason, it's like Euclidean CFT, which lives on sphere, right? D-dimensional sphere. Okay. And for the Euclidean, no time. And DS, Bonita space, maybe let's talk about DS3, so then metric looks like this. dt square hyperbolic cosine square and d omega square, d omega. Well, maybe if you want that explicitly, it's a polar coordinate like this. So this means that, so we have some sphere exponentially expanding, but usually we start at t equals 0. T equals 0, we continue to Euclidean space, and this case is S3. This half semi-sphere. But this part, exponential growth is given by this. This is S2, right? Two-dimensional sphere is exponentially expanding. And t goes to infinity, we cannot write expression, but S2 appears. And the SCFT, it claims that this universe, right, gravity on this universe is equivalent to some conformal field that lives on S2. But the problem is that, right? The basic problem is that, so this is, CFT is defined in Euclidean space, no time direction. But time is somehow gets, right, appeared by some in an emergent way, right? So how we can get time from no time space? That's the essential problem. And of course, but in other words, this is more non-trivial, and very many people excited about this, of course. So this maybe we can, if we solve this, then maybe we can understand origin of time direction. So it's quite interesting, but yeah, what I can just quickly mention what is known, and so what about that? I cannot answer precisely, but what is known about this. I'm talking about DS3. Then we can use 2D CFT as the dual 2D CFT. So then we can see that first the central charge of this 2D CFT is turned out to be imaginary. So again, there is a radius, RDS square, and this is a metric, and RDS, and 2G Newton constant. So it's like turned out to be imaginary. So you can just calculate it. Now you can. The reason why we have this funny I is because anyway here we have Lorentzian theory, right? Lorentzian gravity. You can calculate partition function. ds partition function or wave function is equivalent to CFT. This includes I somehow because it's a Lorentzian calculation. And in terms of the CFT is Euclidean, right? Then for this I always should be marginal. That's the reason you get that idea. So we get, and this should be, but it is true. So first point, this should be large. So this 2D absolute value should be very, very large in order to have a large radius. So that sense, the first point is same. Second point may be same, but I mean, to answer the second point, we need more details, to be honest. We need a more interacting models.
Do we think of DSCFT2 as an ADSCFT2 with some big rotation?
Okay, yes, exactly so. So you can start from this, or maybe, okay, let me start with the Poincare coordinate. So we talk about like this. Now let's talk about like this. So this is a Euclidean version, and we take R squared minus ds. That means we go ADS radius is I times the ds radius, then ds square minus dz square minus rds square, and okay, this square dxi, and then what we do is z Z goes to IT or something. Then this guy becomes ds square minus dt square, t square, dx by dx. Okay? So this is, quantum coordinate of logical space-time. And that's actually equivalent to ADS, Euclidean ADS. And by this transform, this is maybe fun, but this is really radius becomes imaginary. So very formal procedure, but they are really. But you have to be careful if you want to calculate 2-point function in logical space, anti-logical space, and map by this guy. Actually, that's our recent work also. But you don't get proper 2-point function.
You don't
in the bulk. In the bulk. It's given. You need to take a linear because it's sort of related to some CPT invariance. CPT no, logical space, it looks like this, right? And you can slightly extend. Original this spectrum goes this way. And there's antipodal mapping. You can correlate these 2 points. Right? North pole and south pole. Or this point, this point. And there is argument that we should always gauge this symmetry. And then you can get proper 2-point function. That's actually a recent work of that. So there is such a subtle issue, but formally you can take analytical conjecture. In many cases it works, but some cases don't work. Okay. And maybe because I talked about this DSFT, so as a final example, maybe let me mention that entropy calculation in this case. So holographic entanglement entropy in the CFT. So there is a nice work by Narayan several years ago, and there is some problem. Some confusing aspects which we can notice that. So we have like this. So if we want to calculate the entanglement entropy, so what we do is, so we talk about subsystem A. So this is, we have sphere, right? But you can imagine this is time, right? We don't care. So the sphere, but this is time direction, and you can talk about subsystem A. And this is subsystem A, and then we can talk about the entanglement entropy. If there is a CFT, if this is DSCFT is correct, there is a CFT there, and there should be some entanglement entropy. But that means we can just pick up these 2 points and calculate minimal surface, extremal surface. But the extremal surface in this case, DS3 case, let's talk about DS3 case, it's just geodesic line. And geodesic length, we know geodesic length formula in DS3. And if you continue that space, but the point that there are no this kind of space-like geodesic which connect these 2 points. Accordingly, if you plug this position into famous geodesic formula, you get a complex value. And if we interpret this complex value, it goes like this. It's going here, and they connect around this sphere. So it takes this form. SA, so SA looks like this, 3 over I something, but it's like, okay, but it's like 3 over C maybe. Yeah. To the log of something, sine theta something, something. And also, like 2 pi pi over the Newton, L, R, ds or something. So the point is that this guy is imaginary, right? So we talked about ds. Nicely, this central charge appears. This is a well-known formula also to the CFT. Looks like, forget about this one. This is a quite well-known formula for usual CFT. But now we have to replace central charge with this imaginary value. So this imaginary term comes from this time-like geodesic. Because the space-like geodesic contributes real value to the entropy, but time-like geodesic contributes the imaginary. Right? It's like square root of g. And if this becomes time minus, so it looks like imaginary. And this final piece is given. This is a half of logical entropy. If we go around, right, then it's like logical entropy is just half, right? Just half. So, okay, so this way, so you can calculate this sort of holographic entanglement, and it's at least formally agree with what we expect from 2D CFT. But here, our point is that in one of our recent work, we emphasize that in this setup, I mean, because this is a complex value, this is no longer entanglement entropy, because the entanglement entropy should be non-negative quantity. So this is should be more properly understood pseudo entropy. Pseudo entropy is defined this way. So pseudo entropy is defined the following way. So we take two different states. So we talk about some transition matrix. These are two different states, psi and buffer. This is the initial state and the final state. This is initial state. This is final state. And so tau, and we have reduced density matrix, and it's given by this tau. Okay? And then compute entropy, pseudo entropy as a minus tau rho tau. Tau rho. This if we replace this tau with rho, is just a fundamental, right? So you could, these two are the same, right? This is just one because it's inner product. Then it's just the same as the entanglement. But these two are different. So this is the pseudo entropy, and in this case, why we have pseudo entropy? Because we have this Tojita dual CFT. But as we noticed that there is an imaginary central charge. Like path integral always imaginary something. So that means this state, and usually this state and this state you can regard it as a psi and buffer, as a psi and psi, blah, okay? It's conjugate each other. But actually it's turned out because of I, you take a conjugate state as a minus sign, but this is a plus sign. Both are plus sign. So this is like in terms of star state. It's different state. So that's the reason we need pseudo entropy, and this quantity can be generically complex value. This is a complex value because this is not Hermitian. This is not Hermitian. Non-Hermitian. So this is probably interesting quantity applicable to non-Hermitian system. Thanks. So, and the reason why we talk about this pseudo entropy, this is a final point. So you can actually compute this also in ADSFT. If you talk about Euclidean time dependent ADS. Previously, I talked about this covariant prescription is about the Lorentzian time dependence, but here I'm talking about Euclidean time dependent ADS. Then holographic entanglement. Maybe you might think this minimal surface looks like holographic entanglement. Also here, right? You can just slightly time dependent, but essentially same. So some Euclidean ADS, and we have some time dependence, but you can always define nice minimal surface because everything Euclidean, right? Time direction is now imaginary time, but there is a non-trivial imaginary time evolution. Actually, if you completely path integral, you get to some inner product between two different states. It's equal to this Euclidean time. It's like a Tondelian. But this quantity you can easily calculate in this time dependent Euclidean ADS background, but this is not entanglement. It actually should be understood that pseudo entropy is exactly given by this. Because the states are different. This path integral and this path integral initial from minus infinity to 0, this creates one state. Okay? But the other path integral from plus infinity, this defines two different states. And just using this formula, and you get this. You can precisely match. So this is one of my recent interests. Yeah, I think you're probably. Thank you very much.
So do you have any questions? Questions? So in that case,
Yeah. So, what will be the state counting interpretation in the extremal black holes? Like beta is 0, beta is 0 for the extremal black hole. So how do you have a state counting interpretation in the CFTs? Like
Okay. So, but yeah, extremal black hole in, for example, 5D in flat space is interpreted as a BTG black hole in 3D.
Right.
And in that case, actually, it's like 3D BTG has a 2 parameter. It's like, because in there it's a kind of rotating black hole. So you have an energy and angular momentum, and mass. And actually, extremal black hole corresponds to these two by the same.
right.
And you can just use this formula. That means that you have a two density matrix in 2D CFT language. You have energy. Actually, you have some beta H, and chemical potential J, right? And in that case, I think you can take these two guys the same.
So the combination basically matters.
Special combination. Yeah, and that's ensemble. It's a sort of very similar to thermal state, but it is angular momentum. That describes 5D extremal black holes. That's one answer.
One more thing is that you talked about the strong coupling limit when GS is going to when the two coupling is going into infinity, right? So does that causes the gap in the spectrum for the black holes? Like for the black holes you have some low line states,
Okay, you're right.
and for the high line states that is corresponding to the black holes.
That's right. That's equal. So we have low energy states,
Right.
and because of strong coupling,
Yes.
so many states are going up, lifted, and ideally we get some. Because anyway we have a black hole, right? That
Right.
means above this is a black hole mass. Above I think C over 12 or something. Above that, this is I'm to the area 3, right? In the Hamiltonian. And above that, there should be infinitely many states because the black hole states are a lot of them. But it's possible that we can have no states below. This is ideal situation. But so far, I think many people try to construct this theory, not completely successful. But in general, in supersymmetric case, there are some states, number of states, but this is very sparse. You can show that this is very, you can estimate how many states are there. If we assume that there is a nice black hole description,
Yes.
that gives some constraint on the number of states. That is called sparseness condition. Yeah, that's also.
Any other question?
So, while adding corrections to the entropy of a region, of a black hole, we have a term which corresponds to a term proportional to the area, plus some extra thermal corrections.
Both are,
Yeah, so-
area, proportional area,
Yeah, plus some thermal corrections. So those thermal corrections, because we have a UV cutoff, so we have like an epsilon scale. So when we said that, we can when we try to compute the entropy on the a boundary of some area, we may get divergences. But if we have that epsilon scale, then we can avoid divergences. But is it possible to not introduce that epsilon scale? But since we are only concerned with changes in entropy, anyways, right? We have a function which gives us the actual value, but ultimately we are concerned with changes, right? So if we have a way to regularize this where we have divergences, but we take differences anyways, so the difference is still the finite value.
But anyway, this divergence is kind of difficult to avoid because you have some black hole horizons like this, always this kind of nearby black hole horizons look windlessness. It's from you have a black hole, but outside of observer there is a time direction, usual time direction that looks like this way. Time direction somehow looks like this. Nearby black hole horizon. This is a horizon. And that means that actually effective temperature for this observer, right? It's actually goes to infinity if you go to really nearby horizon. So this divergence just comes from observer's temperature. So you have to integrate this degree of freedom, this degree and up to this point. And that's the reason we get the epsilon divergence which I mentioned. So actually we cut out this region somehow in the calculation. So yeah, I don't think so. It's not so easy to remove that divergence in gravity calculation. If you give me thermal contribution, even though it's thermal, but the thermal temperature gets divergent. It's observer dependent. This is called undo effect.
What is it?
Undo.
Oh, under.
Undo effect. So it's an observer dependent temperature. And some observer which is very close to the horizon has an infinite temperature. And because of infinite temperature, of course, right, and entropy divergence, right? Because the entropy is somehow proportional to some power of temperature. So maybe we can cut out space time. That was one possibility.
Yeah.
Anything else?
I guess we can conclude now.